Imagine an engine with no crankshaft, no connecting rods, no camshaft, no valve train, just pistons bouncing freely back and forth like pinballs in a machine, generating power through pure controlled chaos. It sounds impossible, like something that would tear itself apart in seconds. But in 1928, while Detroit was perfecting the conventional engine we all know today, a Swedish engineer named Birger Ljungström built exactly that, and it worked better than anything coming out of Motor City. This is the story of how one Swedish inventor created an engine that defied every engineering convention of his time, achieved efficiency levels that would not be matched for decades, and proved that sometimes the best solution is the one nobody else was crazy enough to try. It is also the story of why you have probably never heard of it, and why Detroit made absolutely sure it stayed that way. The problem with normal engines. To understand why Ljungström's invention was so revolutionary, we need to understand what everyone else was building in 1928. The internal combustion engine had been around for about 50 years. The basic architecture was settled science. Pistons moved up and down in cylinders, connected by rods to a rotating crankshaft. The crankshaft converted that linear motion into rotation. A camshaft, geared to the crankshaft, operated valves to let air and fuel in and exhaust out. This design required precise tolerances. The connecting rod bearings had to handle tremendous forces, thousands of pounds of pressure trying to bend and break them with every combustion event. The crankshaft itself was a massive, complex piece of forged steel that had to be perfectly balanced, or it would shake the engine apart. The valve train added even more complexity. Springs, rockers, push rods, all moving in perfect synchronization, or the engine would destroy itself. By 1928, manufacturers had gotten pretty good at building these engines. A typical car engine had around 300 moving parts. Efficiency hovered around 25%, meaning 3/4 of the fuel's energy went out the tailpipe as waste heat. Everyone accepted this as the cost of doing business. Engines were heavy, complex, inefficient, but they worked. And here is the thing. Nobody was really questioning this. Why would they? The architecture had been proven. Millions of engines were being built this way. Engineers had spent decades refining the details, bearing materials, crankshaft counterweights, valve spring rates. The industry had invested billions in tooling and expertise around this basic design. Questioning the fundamental architecture was not just radical, it was professional suicide. Detroit's engineers wore white shirts and skinny ties. They worked in massive research facilities with precision measurement equipment. They had PhDs in mechanical engineering. They knew with absolute certainty that the reciprocating piston engine connected to a crankshaft was the optimal solution. Any other approach was either impractical, unreliable, or both. This was not arrogance. It was the accumulated wisdom of 50 years of automotive engineering, or so they thought. Enter Birger Ljungström, the outsider. Birger Ljungström looked at this whole system and saw unnecessary complexity. Why did you need a crankshaft at all? What if the pistons could just move freely, bouncing back and forth on cushions of compressed air? What if, instead of trying to convert linear motion to rotation mechanically, you used the compressed air to spin a turbine? Here is where it gets interesting. Ljungström was not an automotive engineer. He was a turbine specialist. He had made his name designing steam turbines for power generation. He understood thermodynamics and fluid dynamics, but he had not spent decades being indoctrinated into the church of the crankshaft. He did not know what was impossible, because nobody had told him it was impossible. This is crucial. Sometimes the biggest breakthroughs come from people who do not know enough to know they should fail. Ljungström had been working on steam turbines when he started thinking about internal combustion. He noticed that conventional engines were doing something incredibly wasteful. They were converting linear motion to rotation, then often converting that rotation back to linear motion for things like compressors and pumps. Why not just keep it linear and let pistons do what pistons naturally want to do, move back and forth, and capture that energy directly? The concept hit him like a lightning bolt. two pistons in a cylinder facing each other. No connecting rods. No crankshaft. When fuel combusts between them, they fly apart. The compression on the backside of each piston creates an air spring that bounces them back together. They collide, not physically, but the air between them compresses until it auto-ignites the fuel. Boom! They fly apart again. The cycle continues. The free piston concept was stupidly simple. But here's the genius part. The thing that separated this from being just another failed experiment. The pistons were not just bouncing around for fun, wasting energy in pointless oscillation. Each stroke compressed air in secondary cylinders attached to the main combustion chamber. That compressed air was channeled to a turbine through carefully designed passages. The turbine spun a generator or drove whatever needed driving, a ship propeller, an industrial compressor, or other machinery. The pistons themselves never touched anything except the cylinder walls. No bearings, no connecting rods, no mechanical linkages whatsoever. They just bounced back and forth on cushions of compressed air, converting chemical energy directly into compressed air, then into rotational power through the turbine. Think about that for a second. It was almost stupidly simple in concept, the kind of idea that makes you wonder why nobody thought of it earlier. Take two pistons, put them in a cylinder facing each other, let combustion push them apart, let compressed air bounce them back together, repeat. That is it. No complex mechanical linkages that require precise machining and constant lubrication. No timing mechanisms with chains and gears that can slip or wear. No carefully balanced crankshaft that costs a fortune to manufacture and fails if mishandled. Just controlled explosions making pistons bounce back and forth like the world's most violent pogo stick. Of course, saying it is simple and making it actually work are two very different things. Like saying brain surgery is just careful cutting. Ljungström spent years developing the details that made the concept practical. How do you start the pistons bouncing in the first place when they are just sitting there at rest? How do you control the bouncing frequency to match the load requirements? How do you synchronize multiple cylinders so they are not fighting each other? What happens when the load changes suddenly and the pistons need to find a new equilibrium? How do you prevent the pistons from smashing together and destroying themselves when something goes wrong? These were not trivial problems. They were serious engineering challenges that would have stopped most people cold. But they were engineering problems with engineering solutions, not fundamental flaws in the concept itself. Ljungström solved them one by one through testing, iteration, and an understanding of thermodynamics that was decades ahead of his time. The engineering advantages were absolutely staggering. No crankshaft meant no main bearings to fail. No connecting rods meant no rod bearings to wear out. No mechanical valve train meant no timing issues. No valve float at high speeds. And no cam wear. Ljungström had eliminated about 80% of a conventional engine's moving parts. Let me repeat that. He had taken an engine with 300 moving parts and reduced it to maybe 60. The maintenance implications alone were mind-blowing. In a conventional engine, the bearings were consumable items. They wore out. You had to replace them. The valve train needed constant adjustment. Springs broke, push rods bent, timing chains stretched. The free piston engine had none of these problems. The only things that moved were the pistons themselves, floating on air cushions. There was nothing to wear out except the cylinder walls, and even those saw less stress because there was no side loading from connecting rods. But the real genius was in the compression ratio. In a normal engine, the piston has to stop at exactly the same point every revolution because it is tied to the crankshaft. The compression ratio is fixed. Too high and the engine knocks itself to death. Too low and you are leaving efficiency on the table. It is a compromise, always a compromise. Ljungström's pistons had no such limitation. They compressed until the pressure and temperature were perfect for ignition. Then boom. If the fuel quality changed, the pistons automatically adjusted their stroke. Running on low-grade fuel, the pistons would bounce closer together to achieve the same compression pressure. With high-octane racing fuel, they would bounce with a longer stroke, extracting maximum energy. The engine was self-optimizing. It adapted to whatever fuel you fed it without any manual adjustment. This was 1928, remember? Fuel quality varied wildly. Gas stations sold whatever came out of the refinery that week. An engine that could automatically adjust to fuel quality was worth its weight in gold. The numbers were astonishing. For 1928, while Detroit's best engines were achieving 25% thermal efficiency, meaning 75% of the fuel's energy was wasted, Ljungström's free-piston engine hit 50%, double the efficiency, half the fuel consumption for the same power output. In an era when fuel economy was not even a selling point, Ljungström had accidentally created the world's most efficient internal combustion engine. The power-to-weight ratio was equally impressive. Without a heavy crankshaft, flywheel, or valve train, the free-piston engine weighed about 40% less than a conventional engine of the same power output. The Swedish State Railways tested one of Ljungström's engines in 1934. A unit weighing just 2,200 pounds produced 140 horsepower continuously, with peaks of 200 horsepower. A comparable conventional diesel weighed nearly 4,000 pounds. Detroit's reaction: fear and dismissal. So why did Detroit not immediately license this technology and revolutionize the automotive industry? Why are we not all driving free-piston cars today? The answer involves engineering prejudice, industrial inertia, and a healthy dose of not-invented-here syndrome. When Ljungström's patents started circulating in engineering circles, the response from American manufacturers was swift and dismissive. General Motors' research division wrote a scathing internal memo in 1932, calling the free-piston engine theoretically interesting but practically useless. Ford's engineers were even less diplomatic, with one senior engineer calling it Swedish nonsense that violates fundamental principles of mechanical design. The criticism centered on control. In a conventional engine, everything is mechanically synchronized. The pistons move in lockstep with the crankshaft. The valves open and close at precisely determined intervals. Engineers could calculate exactly what would happen at every degree of rotation. They could draw it on paper. They could predict it with mathematics. It was deterministic. It was controllable. It was safe. Ljungström's free-piston engine was probabilistic rather than deterministic. The pistons bounced at their natural frequency, which could vary slightly with temperature, altitude, or load. This terrified Detroit engineers, who had spent decades perfecting mechanical precision. How do you tune an engine when you cannot predict exactly when combustion will occur? How do you synchronize multiple cylinders when each one is operating at a slightly different frequency? How do you even measure performance when the engine is constantly adapting? These were not stupid concerns. They were legitimate engineering challenges, but they were challenges that could be solved with clever design and proper instrumentation. Detroit's engineers did not want to solve them. They wanted to dismiss the entire concept as impractical and get back to their familiar crankshafts and camshafts. There was also the sound. A conventional engine has a regular rhythm: bang, 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 bang. It is musical in a way. Ljungström's engine sounded like controlled chaos. The pistons bounced at around 50 cycles per second, creating a high-pitched buzzing that one observer described as a giant angry hornet trapped in a metal box. The exhaust note was a continuous turbine whine, rather than the familiar puttering of a conventional engine. Market research in the 1930s suggested American consumers would reject any car that did not sound normal. Americans wanted their cars to sound like cars, not like industrial machinery. Never mind that the free-piston engine was more efficient, more reliable, and more powerful. It did not sound right, so it would never sell. At least, that is what Detroit told itself. Industrial inertia killed innovation. But the real nail in the coffin was industrial momentum, the unstoppable force of sunk costs and established processes. By 1928, Detroit had invested millions, maybe billions in today's dollars, in tooling for conventional engines. Entire factories were dedicated to forging crankshafts, massive drop forges that cost fortunes and did one thing perfectly: They cast cylinder heads in sand molds, processes refined over decades. They machined camshafts on specialized equipment that could not be repurposed for anything else. These were not just factories, they were entire industrial ecosystems. Thousands of engineers knew how to design conventional engines. They had spent their careers mastering valve timing, optimizing combustion chamber shapes, calculating bearing loads. Their expertise was valuable precisely because it was specific. Supply chains delivered conventional engine parts, warehouses full of pistons and rings and bearings and gaskets. Mechanics knew how to fix them, could diagnose problems by sound, could rebuild them blindfolded. Trade schools taught students how to work on them. Entire curricula built around the conventional engine architecture. Switching to free-piston engines would have required scrapping all of that infrastructure and expertise. Every factory would need new tooling, new equipment, new processes. Every engineer would need retraining. Years of accumulated knowledge, suddenly obsolete. Every mechanic would have to learn a completely new technology with no reference points. Every part supplier would have to retool their entire operation. Every trade school would have to rewrite their curriculum. The cost would have been astronomical, catastrophic, potentially industry-destroying. Gasoline cost 15 cents a gallon. To improve efficiency, when nobody cared about efficiency because fuel was cheaper than water. To reduce parts count when parts were cheap and labor was cheaper. The business case did not exist. The market did not demand it. Customers were not asking for it. Shareholders would have revolted. Let that sink in for a moment. An engine that was twice as efficient, weighed half as much, and had 80% fewer parts was rejected not because it did not work, but because it would have been too disruptive to the existing industry. This was not a technical decision based on engineering merit. It was a business decision based on protecting existing investments. Detroit chose protecting their investment over pursuing better technology. They chose the familiar over the optimal, the incremental over the revolutionary, the safe over the superior. And they justified it with technical objections that sounded reasonable, concerns about reliability and durability and customer acceptance that were really just excuses. The real reason was simpler and more cynical. Changing would cost too much money, and nobody was forcing them to change. So they did not. Where it actually succeeded was in submarines. But Ljungström's invention didn't die completely. While Detroit ignored it, other industries paid attention. The French company Sigma, Société Industrielle Générale de Mécanique, licensed Ljungström's patents in 1938 and started serious development. They saw applications where the free-piston engine's advantages outweighed its unconventional nature. Submarines were the perfect example. In a submarine, every cubic inch of space matters. Every pound of weight reduces diving depth. Efficiency directly translates to underwater range. Sigma developed a free-piston engine specifically for submarine air compressors. Instead of using a conventional diesel to drive a mechanical compressor, two separate machines with hundreds of parts each, the free-piston engine compressed air directly. One machine doing the work of two, at half the weight and twice the efficiency. The French Navy installed Sigma free-piston units in several submarines before World War II. The Germans, after occupying France in 1940, captured some of these boats and were so impressed they ordered Sigma to continue development under occupation. The GS-34 free-piston compressor, developed in 1942, could charge a submarine's air banks to 3,000 PS1 in half the time of conventional systems, while burning 40% less fuel. German U-boat commanders reported the units were virtually maintenance-free, running for thousands of hours between overhauls. Think about that environment, a submarine where you can't exactly stop for repairs, where reliability is literally life or death. The free-piston engine thrived where conventional engines failed. Because when you're 300 feet underwater being depth-charged by destroyers, you don't care what the engine sounds like. You care if it works. The post-war applications. Sigma's most successful free-piston engine was the GS-34. introduced in 1950. This was not some experimental prototype. It was a production engine, manufactured by the hundreds. The specifications were remarkable even by modern standards. The engine had just two moving assemblies, the opposed pistons. No crankshaft, no connecting rods, no camshaft, no valves. Total parts count was 37. A comparable conventional diesel had over 300 parts. The GS34 produced 50 horsepower continuously, with short-term outputs of 75 horsepower. It weighed 420 pounds, complete with turbine and generator. Thermal efficiency reached 45% when contemporary car engines were still struggling to break 30%. Maintenance consisted of changing the oil and cleaning the air filter. That is it. There were no valve adjustments, no timing chains to replace, no bearing clearances to check. French industrial plants used GS34 units as emergency generators well into the 1970s, with some units logging over 50,000 hours of operation. 50,000 hours. That is nearly 6 years of continuous operation, a testament to reliability. Show me a conventional diesel from 1950 that could do that without a major overhaul. The free piston principle also found applications in more exotic machinery. Alan Muntz, a British engineer who had worked with Ljungström, developed a free piston engine for torpedo propulsion in 1943. Instead of compressed air driving a turbine, high-pressure combustion gases were expelled directly through a nozzle, creating thrust. No turbine, no propeller, no shaft, just controlled explosions pushing the torpedo forward. The British Admiralty tested Muntz's engine, but ultimately decided it was too radical for wartime adoption. Too risky, too different. Sound familiar? The most ambitious free piston project was the Pescara engine, developed by Spanish engineer Raúl Pateras Pescara in the 1940s. Pescara took Ljungström's concept and scaled it up massively. His engine used multiple free piston units arranged in a star configuration, all feeding compressed gas to a central turbine. The PP-12 engine, tested in 1948, had 12 free piston cylinders and produced 2,000 horsepower. It weighed 4,400 pounds, about the same as a conventional radial aircraft engine of half the power. Pescara claimed his engine could run on anything combustible, including gasoline, diesel, kerosene, and even powdered coal mixed with oil. The free pistons automatically adjusted their compression to suit whatever fuel was available. The Argentine government funded development, seeing potential for an engine that could run on their domestic crude oil without refining. Test runs confirmed Pescara's claims. The engine ran successfully on crude oil straight from the wellhead, something no conventional engine could manage. What killed it? Starting was tricky. You had to get the pistons bouncing at exactly the right frequency, or they'd either stall out completely or crash together and turn themselves into scrap metal. Sigma solved this with compressed air starters that gave the pistons a precise initial push to get the oscillation going. Synchronizing multiple cylinders required careful design of the air passages to ensure equal flow resistance. Otherwise, one cylinder would be bouncing happily while another sat there doing nothing. Load changes could cause momentary instabilities as the pistons found their new equilibrium, hunting for the right frequency like a radio trying to lock onto a station. But these were engineering problems with engineering solutions. Smart people with time and money could have solved them. The starting issue? Electric motors could have done the job. Synchronization, better manifold design, load stability, feedback controls, even mechanical ones available in the 1950s. None of this was impossible. It was just different, and different is expensive when you're trying to build an industry. The real killer was the gas turbine. By the 1950s, aircraft gas turbines were becoming reliable and efficient. The jet age had arrived, and with it came massive investment in turbine technology for military and commercial aviation. They offered the same advantages as free piston engines: few moving parts, high power-to-weight ratios, multi-fuel capability that let them run on anything that burned. but with smooth operation that didn't sound like an angry hornet, and with established manufacturing infrastructure paid for by defense contracts. Why develop exotic free-piston technology when you could adapt existing jet engine technology that the government had already spent billions perfecting? For automotive applications, the death blow came from emissions regulations. Free-piston engines, with their variable compression and probabilistic operation, were nearly impossible to tune for consistent emissions. The combustion process varied slightly with every cycle based on temperature, load, atmospheric pressure, dozens of variables. There was no fixed timing to optimize, no cam profile to adjust, no way to guarantee that cylinder number 3 would burn exactly the same way every single time. When the Clean Air Act hit in 1970, demanding consistent, measurable, repeatable emission levels, even conventional engines struggled to meet standards. Manufacturers spent millions developing catalytic converters and electronic fuel injection just to keep their existing engines legal. Free-piston engines never had a chance. How do you certify an engine that operates differently every cycle? How do you prove compliance when the combustion event is fundamentally probabilistic? The EPA wanted predictability. Free-piston engines were chaos, controlled chaos maybe, but chaos nonetheless. The regulations killed them more effectively than any technical limitation ever could. The modern resurrection. But here is the thing about ahead-of-its-time technology. Sometimes the world catches up. In 2014, Toyota unveiled a free-piston engine linear generator at the Geneva Motor Show. Instead of driving a turbine, the pistons drove linear electric generators directly. No rotating parts at all. Toyota claimed 42% thermal efficiency, not quite matching Ljungström's 1928 design, but impressive for a modern engine meeting current emission standards. The German Aerospace Center developed a free-piston engine in 2016 specifically for range-extended electric vehicles. Their design used opposed pistons driving a linear generator, producing 35 kilowatts of electrical power from a package the size of a large suitcase. Thermal efficiency was 46%. Weight was 65 kilograms. Parts count was under 50. Mainspring Energy, a Silicon Valley startup founded by former Tesla engineers, raised $150 million in 2020 to commercialize what they call a linear generator, essentially a modern free-piston engine optimized for grid-scale power generation. Their design claims 45% efficiency running on natural gas, biogas, or hydrogen. The company promises maintenance intervals of 20,000 hours, about 10 times longer than conventional generators. Even Formula One briefly considered free-piston engines. In 2013, when the FIA was developing new engine regulations, Ferrari proposed allowing free-piston range extenders for hybrid race cars. The idea was rejected as too radical, but Ferrari's engineers ran simulations showing a free-piston generator could be 30% lighter than the conventional MG/UK units currently used. The irony and legacy is almost delicious. Nearly a century after Detroit dismissed Ljungström's invention as impractical Swedish nonsense after American engineers allegedly called it a violation of fundamental mechanical principles, the same basic principle is being pursued by some of the world's most advanced engineering companies. Toyota, Tesla alumni, German aerospace contractors, they are all chasing what one Swedish turbine guy figured out in 1928. The difference now is electronic controls that can manage the probabilistic nature of free pistons, materials science that can handle the stresses without catastrophic failure, computer simulations that can optimize the bouncing frequency without years of trial and error, and, most importantly, a market that actually values efficiency over convention. Think about that for a second. In 1928, one man working in Sweden created an engine architecture that was so efficient, so fundamentally correct, so ahead of its time that it took the rest of the world 90 years to catch up. 90 years. Ford went from the Model T to the Mustang to bankruptcy and back. General Motors rose and fell, and rose again. Entire automotive empires were built and destroyed. And Ljungström's basic concept, dismissed as impossible in its time, is now being validated by companies with billion-dollar research budgets. Ljungström did not just optimize the existing paradigm. He did not just make the conventional engine a bit better. He threw it out completely and started from first principles. What does an engine really need to do? Convert fuel into motion, that is it. Everything else, all those crankshafts and camshafts and valve trains and timing chains, was convention. Accumulated complexity that everyone assumed was necessary because that is how it had always been done. The free-piston engine story is really a story about innovation and inertia, about how industries become locked into particular solutions, not because they are best, but because they are established, because the factories are already built, because the engineers already know how to design them, because change is expensive and risky. This is about how truly revolutionary ideas often come from outsiders, people who do not know what is impossible. They have not been trained to think inside the box, because they do not even know the box exists. Ljungström was not an automotive engineer. He was a turbine specialist who happened to wonder why reciprocating engines were so complicated. He did not have years of internal combustion experience telling him what would not work. He just had first principles and a willingness to try something completely different. It is also a reminder that efficiency matters, even when nobody thinks it does. In 1928, when oil was cheap and abundant and climate change was not even a concept people could imagine, doubling engine efficiency seemed like an academic exercise, interesting but not particularly important. Today, with every percentage point of efficiency translating to millions of tons of carbon dioxide saved globally, Ljungström's work looks prophetic. He solved a problem we did not know we had and answered a question we had not thought to ask. The Swedish inventor who outsmarted Detroit did not live to see his vision validated. Birger Ljungström died in 1979 at age 87. His free-piston engine was remembered mainly as an engineering curiosity, a footnote in textbooks about alternative engine designs. But every time a modern engineer looks at a conventional engine and thinks there must be a better way, they are following in Ljungström's footsteps. Sometimes the best solution is not an improvement on what exists. It is something completely different. Today, as electric vehicles threaten to make all internal combustion obsolete, there is something poetic about the free-piston engine's resurrection as a range extender and generator. The technology that was too radical for the age of gasoline might find its place in the age of electricity, not as a competitor to batteries, but as their partner, converting fuel to electrons with an efficiency auto and diesel could only dream of. What other revolutionary technologies are sitting in patent archives, dismissed as impractical by industries too invested in the status quo to change? What modern-day Ljungströms are working in workshops right now, building impossible machines that actually work better than what we have? The free-piston engine teaches us that sometimes the experts are wrong. Sometimes the established way is just the established way, not the best way. And sometimes it takes an outsider with a weird idea to show us what we are missing. Birger Ljungström was that outsider. His weird idea was bouncing pistons with no crankshaft. And 90 years later, the world is finally admitting he was right all along.